2, 1. Alright, another 2070 video, the online section of matrices and linear algebra right here at Iowa State. Alright, so today we're going to keep going down the eigenhole, and we are now going to return to linear transforms and talk about a nice little connection between those and eigenvectors. Alright. So let's revisit linear transformations for a moment, and let's look at a linear mapping from a vector space to itself. And let's say I've got a basis B1 to Bn. Okay. Well, any element in our vector space then is a linear combination of those basis elements. In fact, it's a unique linear combo, so I can create the coordinate vector by taking those scalars and just going, hey, here's the scalars associated with that element x. Well, T is a linear mapping, so when I feed T this input, it pulls apart the scaling and the adding, and hey, look at that, T of x is equal to this beautiful little linear combo. The coordinate mapping we know is linear itself, so if I want to get the coordinate mapping for T of x, well, then it is this linear combo right there. And letting M be the matrix that has these as its columns then gives me this relationship between the coordinate vector for our input and the coordinate vector for our output. There's a matrix that lets me jump between the two. And obviously, we then call this the matrix for T relative to the basis, and we denote it by T sub B. All right, so we now have a way of talking about any linear transform on an arbitrary vector space and in converting it over to a matrix that we can work with. So let's get some examples. Suppose I have B1, B2, a basis for vector space V, and I've got a linear transform T, and I know what this linear transform does to my basis elements. It sends B1 to 7B1 plus 4B2. And it sends B2 to 6B1 minus 5B2. All right, so note the coordinate vector for TB1 is simply 7, 4, because that's the scalars associated with my basis B1, B2. Likewise, the coordinate vector for TB2 is 6, negative 5, because of the scalars there. And so the matrix for T with respect to B is just these as their columns. All right, hey, nice and easy. All right, let's get a little spicier. Let's let T be the mapping that takes a polynomial of degree at most 2, so an a, bt plus c, t squared, and it mutates the polynomial as follows, so it does a lot to it. Now, this is a linear mapping, and we know that P2 is basically R3, and so if you've got a linear mapping from R3 to R3, that means there should be a 3 by 3 matrix that describes this. All right, well, if I want to get the matrix representation relative to the standard basis for our polynomials, well, you plug in the standard polynomials into the linear mapping, see where they go, and then get the coordinate vectors associated with them. So here, since plugging in 1 will give me the polynomial 2 plus 5t squared, I have a vector of 2, 0, 5. Plugging in the polynomial t is going to give me a 3t, and there we go. Likewise for t squared we get that, and combining all of that together gives me the 3 by 3 matrix that basically is how this linear mapping is behaving. All right, beautiful. Well, the title of the video today is Eigenvectors and Transformations. So I've seen the linear transform side of things. We've revisited linear transforms and got matrices for them. So naturally, we want to connect this to all of the good eigenvalue and eigenvector stuff we've been doing. All right, so last time we talked about diagonalizable matrices. Okay, and remember that you're diagonalizable precisely if you have enough eigenvectors, because the columns of the invertible matrix P are precisely the eigenvectors, and the entries of the diagonal matrix are the corresponding eigenvalues. Now, since P is invertible, that means its columns are linearly independent, which means that the columns form a basis for our Euclidean space. So that means that P has to also be the change of coordinates matrix, meaning that multiplying our coordinate vector by the matrix P gives us our original vector. Note that I multiply both sides of this by P inverse. Now, if T is the linear mapping that multiplies by our matrix A, then the coordinate vector for T of PK there, that's not supposed to be a BK, that's a PK. What's going on? All right, let me fix that. There you go. All right, simply multiplying, there's the fix, multiplying that vector by the matrix A. Well, following this formula here, that corresponds to P inverse A PK. But we, of course, remember that the matrix for T relative to this basis B has to be the one with these as its columns. But as we remembered from the last video, if you have a matrix that looks like this, where the columns are a matrix times the vectors here, well, since the columns of P are those vectors, this matrix is precisely P inverse AP. And hey, that's the diagonal matrix D. Nice. So here we see that if I have a linear mapping generated by a matrix A, and I just so happen to know it's diagonalizable, then its matrix with respect to this coordinate, with respect to this basis, its coordinate matrix, is just the diagonal entries, just the eigenvalues. So, for example, if I have a matrix A here, 5, negative 3, negative 7, 1, I can show that negative 2 is an eigenvalue if that is an eigenvector. Likewise, that's an eigenvalue if that is an eigenvector. So the linear transform that is multiplied by this matrix A, the matrix for this with respect to the basis that is generated by these eigenvectors has to be the matrix that has the associated eigenvalues on its diagonal. So its matrix here is this diagonal one. Ooh. All right, so here we see that if you have a linear transform generated by multiplying by a matrix, you can actually get the coordinate matrix with respect to the basis from the eigenvectors by just getting the eigenvalues. Nice. So, pretty slick little move, and nice little connection here between all of this eigenvalue and eigenvector stuff we've been doing and our good friend linear transforms. Alright, that's all I got for you today. So I'll see you in the next video where we're going to get a little complex.